Welcome to the third video in this jet engine series. In the last video, we saw the governing equations for an adiabatic duct. We go straight into Python here and start the code. Let's dive in.
Trois, deux, un, top.
3, 2, 1, half. The Flight Test Engineering channel.
The link for our GitHub repo is in the description also, but you can search for Flight
Test Engineering, GitHub.
And this should take you straight to our repo here on GitHub. And if you click that and go to the gas turbine propulsion and then turbojet, you see that we have here the episode 2 and 3 Inlet notebook. And if you click there, you'll be able to follow along all the equations and also all of the code is going to be here. If you want to download this, you can also do it by clicking on this button and download the raw file. We start with the preamble here, importing NumPy, matplotlib, setting it to dark theme, and we import Cantera as CT. And then we import the International Standard Atmosphere module as ISA. This is a module that we developed here in our channel in a previous series, and if you haven't watched that, the link is going to be in the description. Note also that we have a commented line here, and hold on to this because we'll come back to this later. So let's run this first cell, and then to check which Cantera version I'm using here, we just run this, this line and we get 3.000. Now, I want to keep the focus of this video on the engine itself. And in order to do that, I put all of the helper functions into this one cell here that we will move to a separate file in just a bit. That's why we have that line over there with the import. Let's briefly go through each function so that you know more or less what they're all about. And if you want to take your time to read through, they are in the channel's GitHub repo. So the link is going to be in the description as well. The first one that we have here is a function that will calculate your stagnation pressure given static pressure, gamma, and your Mach number. We have also one to calculate your stagnation temperature, same idea. This one is the reverse. It calculates the static temperature given your total temperature, gamma, and your Mach number. This is also the reverse. It calculates the static pressure. This one calculates gamma, which is the relationship between CP and CV that we get directly from our Cantera solution. This one calculates R, which is a relation between CP and CV as well, that you get directly from your Cantera solution. This one will calculate the local speed of sound. This one will print the properties of a gas, and we'll see a bit how this works later, but essentially it goes through all the properties that are of interest to us, pressure, temperature, enthalpy, and entropy, and prints it out. And this next one prints all of the properties for a list of stations. And we know that we'll have a few stations in our engine, A, 1, 2, 3, and so forth. This will print all of them up to a point. And this last one will plot a diagram with temperature and entropy. This will be very useful for us to understand what's going on with the transformations on each module. Okay, now that we had an overview of these helper functions, let me cut the contents of this cell and paste it into a new Python file so that we can import. So I'm going to first select everything and cut it. File, new, Python file, and we're going to paste it here. And it's not going to work if we just leave it like this because we need to add here on the top all of the preamble that we had on the other file. When we run this module here by itself to import it, it needs to have Cantera, NumPy, and everything. So let's go back and grab that as well. So we're back here in the notebook. Let's just grab the preamble, Control-C. Let's go to the file that we created over here and paste it on the top. So we come here and just paste the preamble here. And now we're ready to rename this file and save it as, let's call it engine helper functions. Okay, rename. And now we can jump back to the notebook and reset the kernel and try to run it. Okay, we're back on our notebook, so we can come here and reset the kernel and clear everything. We run the cell now to see if it imports everything okay, and it ran. And we can again run the Kantara version. And now all of oh, wait, we need to still uncomment this line to check if we can import everything. And lo and behold, we did import. So everything is working. We have to keep in mind our end goal here. We want to create an engine model. So the first thing we need to do is to create the engine itself, to define it. And parameters like inlet area, nozzle area, they're all physical parameters that we'll place in our engine parameter dictionary here. There are other parameters that deal directly with performance, things like compressor efficiency, turbine efficiency, pressure drop, and these we'll place on the engine performance dictionary like this. And to start, let's say that our engine has an inlet area of 0.3 square meters at station 1, and then we'll also say that the exit area for our station 1 is going to be 0.32. So as we said before, the inlet will act as a diffuser. And lastly, let's say that our eta I for our inlet is going to be 98%. So this is the amount of energy that we will lose as the flow goes through the inlet. Let's skip the next cell and we'll come back later when we have defined the next set of parameters. So let's go to cell number 4 here. We have one more set of parameters that we need to define, which is the engine operating conditions. Things like throttle position, altitude, Mach number. We'll go into this dictionary here, engine opcon. And let's define these conditions here and then get the static pressure and temperature using our ISA imported library that we did before. Given the altitude, we're going to come back and get the static pressure. And then given the altitude, we come back and get the static temperature, for example. Right, like we said, the idea here is that we model each part of the engine. So we need to keep track of what's going on. So let's create a dictionary here for our Kantara solution objects, the gas, and use these stations as keys. And also, let's keep track of the Mach number for each station on this dictionary. Now, let's create a list of the station numbers, which are A for your ambient, and then 1, 2, 3, 4, 5, and 8 for the numbers that we defined before. And to keep track of what's what, let's also create a dictionary with the names of the stations so that we know what is what. So the first one is going to be ambient, inlet, and so forth. Kantara has a general constructor for chemically reacting solutions. At the inlet, we have only air without any reactions, but thinking ahead, we will have fuel reacting when we reach the combustor. So it will be much easier if we plan ahead and use this constructor for our gases. And we'll be doing this shortly. The reaction mechanism is defined using .yaml files, which will have all the necessary parameters for configuration. And in our case, since we're going to burn kerosene, we'll pick the N-dodecane IG file, which is short for ideal gas. And the composition of air will be simplified for oxygen, nitrogen, and CO2 only. And finally, kerosene has between 9 and 16 carbons, so we'll pick 12 for our fuel. So now we're ready to create one object for each station. This is what we're going to do in this loop here. For each of the stations that we defined, we're going to first create the Kantara solution object using the reaction mechanism that we talked about just now, and the phase name, set the composition for pure air, and set the temperature and pressure for the ambient conditions. And also for each station, we're going to define the Mach number as one simple constant for now. And finally, we can start to write our function that will calculate the inlet properties. Let's go back up to that cell that we skipped, this one, and look at what's going on. And we start by defining the inputs here, and we have an important notes. We see that we have m dot going in as the mass flow, the area, the gas is going to be a Cantera solution, eta I the efficiency, the Mach number, and gas out is going to be another Cantera solution. And we're passing Cantera solutions objects here to the function as these two variables, gas in and gas out. And if we change the properties of these gases inside the function, the actual instance will be changed. So we will use this to our advantage and use this variable here, gas out, to pass back the value of the thermodynamic properties for our gas out. As I mentioned before, we'll need to iterate to converge on the properties. So let's first define here the loop control variables. So the tolerance is going to be a value that we'll see what it means when we get to the if statement to check what this means. We'll define a maximum number of iterations, 100 for now. We'll define a Boolean variable to track if our convergence has been reached. So we'll set it to false for now. And this one will track how many iterations we have run through. So we'll start with 0. The input variables, we start to calculate our input number. So from Mach number and the properties of our gas, we get the speed of sound, the local speed of sound, and calculate the actual speed. Also from the gas properties that we're passing in, we calculate what is the gamma and store that on this variable, gamma in. We also calculate what is the temperature of the gas, the total temperature, the stagnation temperature of the gas for the gas going in with its temperature, the gamma that we just calculated, and the Mach number that is coming in. And we store this on our T0 in. And the same for our pressure, or our stagnation pressure is going to be stored here using the function, the helper functions that we defined before. So next, we defined our temperature, stagnation temperature out is going to be equal to our stagnation temperature in. And this derived from our basic hypothesis that there is no heat transfer during this transformation. And next, we define our initial gas for our gas velocity out, and it's going to be our mass flow, m dot, divided by the density times area. And also, we guess that our gamma out is going to be equal to our gamma in. Now we can look at our loop, and it's going to run while it's not converged, and also while the number of iterations is less than or equal to our maximum number of iterations. The thermodynamic properties that we're going to calculate here are first the temperature out, the static temperature out, then the stagnation pressure out, and then the static pressure out. And we're going to use the same formulas that we have seen before, which I've copied here just for convenience. So for instance, the first one is going to be our T out, is going to be our T in plus a kinetic energy term going in minus a kinetic energy term going out, and so forth. Here is the formula for our stagnation pressure out. It's going to be P02, and this one is going to be P2, just per this formula here. Once we have these thermodynamic properties calculated, we're going to use our Cantera solution to calculate the other properties. So first, we update the temperature and pressure of our gas out solution by calling this function here. And then we get the gamma of this gas with the new temperature and pressure that we just updated. So we update our gamma out here. Now we need to update the velocity for the new gas property. So we just store our current velocity out in this variable, saying that it's out equal to our V out gas. And then we calculate a new gas based on the same mass flow, but now with the new gas density that we can obtain through this function here that is also built into Cantera. So Cantera helps us a lot here because we don't have to implement any of these calculations of density and gamma and stuff. And then we check for convergence. So if the absolute value of the difference between our calculated velocity out and our new gas is less than that tolerance that we set, then we're finished. If not, we check if our number of iterations has not reached the maximum. And if not, we add 1 to our number of iterations. And if we have reached the maximum iterations, then we set our Mach number to 0, and we print out a message saying that we have not converged. And finally, we return our Mach out and our flag to say if it's converged. We're ready to run it. So let's jump back down and see what's going on. So the first run that we're going to do is to go from station A to station 1. And remember, this is outside of the duct still. We're still upstream of the engine, just decelerating the gas until it reaches the actual inlet. So what are we passing into our function? We're passing in our guessed m dot, our A1 parameter, which is our area at station 1, our gas at station A, 1 for our centropic efficiency because we're outside of the duct and we are assuming that it's isentropic, the Mach number of the airplane, which is also at station A, and for the output, we're going to use our gas for station 1. And we only add the Mach number to our list if we have convergence. So to run this, let's go back up. And we had stopped here, so let's start our dictionaries. Then we hit return there to load our function. Let's also run our cell here to input all the initial conditions, the initial station setup, and now we can run our cell number 6 here that calculates from station A to station 1. And we see that we had 6 iterations and we have finished and converged. So the next thing we're going to do is to store all the values that we calculated. So we create a few lists here, one for temperature, another one for pressure, and one for the composition of the gas. So here what we're going to do is for x in a range of 0 to 2, because those are the stations that we have so far, we're going to append to these lists the temperature, pressure, and our composition, which so far it's just air. And now on the next cell, we can just print the stations from 0 to 2, the stations' names, the gas, and the Mach number. And we can create our first plot by calling that function that we have seen on our helper, passing in the lists for temperature, pressure, and also our composition, the reaction mechanism, and the phase name, because it will do a few calculations internally to be able to plot the value. So let's see what this gives us. And here we have the first solution, the first results from our iterative function to calculate the inlet. And we can see that we go from station A to station 1, and also that the Mach number goes from 0.8 to 0.469 in this case. And look at the pressure, it goes from 0.24 and increases to 0.31, which we can see here on the diagram as well. So next up, we can go from station 1 to station 2, and now we are inside the duct. So what are we passing in here? Again, our m dot gas. We're passing in our A2 parameter, which is the exit of our inlet, the smaller area. The m gas is going to be the gas that we just obtained from the previous calculation, so it's gas at station 1. The eta, the efficiency of the inlet, is going to be the value that we define for our engine performance parameters. The Mach number is going to be the Mach number that we just calculated as well for station 1. And we're going to store everything for our gas out in our gas 2 for station 2. The same idea here. We only store our values if we have convergence. So if we do converge, we get the number of stations that we have so far. We see the current stations as the last index of our station list. And then for a range that goes from our current station to the number of stations, we just say that our Mach is going to be our Mach calculated. And if we don't converge, then we just print a message saying that we did not converge. And finally, we add to our, remember we had the lists for temperature, pressure, and also the gas composition. We append the values that we calculate on this inlet. So let's run this. And again, we see that it finished and used 4 iterations to converge. And we can do the same thing. We can print the stations now from 0 to 3, which means from stations A, 1, and 2, and also plot the values. So we can see that we went from Mach 0.8, which is our initial condition, to Mach 0.469 at the inlet, and then further down to 0.433 as we are at the face of the compressor, the initial face of the compressor. And here is the temperature and entropy diagram for this transformation, the TS diagram. You can see that inside the inlet, the transformation is very small. And this brings us to the end of this video. As you could see, the equations are not too complicated. However, the need to iterate in order to obtain a solution sets the problem apart. Now that the foundation is set, we can move on. And as always, if you want a copy of this notebook, visit the channel's GitHub page, and the link is going to be down below. On the next video, we'll tackle compressors. See you there!